Good day, viewers. Today, in continuation of our physics lessons, we are going to be having a class on temperature and its measurement. And we'll go straight into the topic. More oftentimes, we hear the word temperature and we get to mix it with heat. Or for a layman, that might be acceptable, but for a physics student, that is unacceptable. Temperature and heat are not the same thing. Temperature helps us to understand how hot or cold a substance is. So we define temperature as a degree of hotness or coldness of a substance. Heat, on the other hand, is a form of energy. When I ask you to list the forms of energy that we have heat, we have electrical energy, we have light energy, we have sound energy, we have mechanical energy. Heat energy is a measure of the total internal energy of an object. Of course, there's a relationship between the two, between heat and temperature. Temperature difference between two objects or substances will help us understand the direction in which the heat will flow. If, for example, we bring two objects together, heat will naturally flow from the one that is hotter to the one that is colder. How do we know the one that is hotter, the one that has an higher temperature? How do we know the one that is colder, the one that has a lower temperature? So generally, heat moves from object with high temperature, with an higher temperature, to an object with a lower temperature. So a difference in temperature creates the condition for the flow of heat from one object to another. Definitely, therefore, when objects have the same temperature, there is no flow of heat between them. So temperature is a degree of hotness or coldness of an object. It helps us to understand how cold or hot an object is. And there are so many numbers that I can give you that are so common. We all understand that the boiling point of water is 100 degrees Celsius, and we understand that generally the body temperature of a normal human is around 37 degrees Celsius. So when you look at the body temperature of a normal human and the boiling point of water, 37 to 100, it helps you to understand why we can say that the boiling water is hotter than the temperature of the temperature of a normal human. So temperature can be measured. But before we go straight into it, I want to talk about the effect of adding heat to an object. We can always add heat to an object from an hotter object. Like I said earlier, difference in temperature between two objects forms a basis for heat to flow from an object to another. When an object now receives heat, what are the things that can happen? What are the effects of adding heat to an object? Number one is that its body's temperature will increase. If an object accepts heat, its temperature will increase. That further will also help us to understand the relationship between heat and temperature. There are so many other effects that it can cause on an object. It can cause what is called a change in state. If an object is solid, if it accepts sufficient amount of heat, it will become liquid, it will melt to liquid. If it is liquid, if it accepts some sufficient amount of heat, then it can also vaporize and become a gas. Also, the reverse of that is possible. If an object loses heat, then it can go from being a gas to liquid. In fact, cooling is one of the methods by which we can condense a gas to liquid. We can also freeze a gas. We can also freeze liquid to solid. There are other effects of heat. For example, when you add heat to an object, it can cause changes in some physical properties. Physical properties are properties that we can easily feel. Things like color, things like shape, things like size, and things like so many other physical properties that can be measured can also change due to the addition of heat on that object. There can be a change in the chemical properties of that substance. There are a whole lot of chemical reactions that take place only when we add heat to the mixed reagents. There are reactions that are called thermal decomposition. We can decompose a substance by just adding heat to it. There are reactions that are also called thermal dissociation. We can completely break a substance into its constituent elements by adding heat to it. There's something that is called thermionic emission. Generally, when we heat some metals, electrons can start to come out of their surface or surfaces. That is called thermionic emission. It is also an effect of heat on an object. When you add heat to gases, it is possible that those gases will try to expand. So expansion, no. When you add heat to substances, they can expand also. Expansion is one of the effects of it. But most importantly, when you add heat to gases, apart from expansion, those gases can also increase in pressure. So the pressure of a gas can increase whenever heat is added. So though it does not affect the pressure of liquid and solids, but it affects the pressure of gases. So if you are going to list change in pressure as one of the effects of it, you must be specific about it. It has to be change in gas pressure. So there are so many other effects of it that we are still going to see later. So when we have temperature, well, temperature can be measured by a substance with a material that is called a measuring device that is called thermometer. Thermometer is something that we will have been hearing about. Thermometer is a material or the device for measuring the temperature of an object. I just showed you that temperature is the degree of hotness or coldness of an object, but there must be an instrument that we can use to measure that exactly. Of course, most of us are in the habit of feeling our body temperature with our palm. That is not reliable. We have to use a more acceptable device for measuring temperature, and that is a thermometer. There are so many thermometers that we have in the world because generally it is easy for you to design an instrument that you can use to measure temperature. Any effect, anything that heat can cause, any change that heat can cause in an object, or in a more appropriate term, any measurable change that heat can cause in an object can be used to measure temperature. Any measurable change that heat can cause in an object can be adapted to the measurement of temperature. One very good example, we know now that anytime we heat a gas, the gas will naturally expand. Anytime we also heat a gas, one of the things that will also happen is the pressure of the gas can change. Because the pressure of the gas can change and I can measure the pressure of the gas, I can adapt that to be used in the measurement of temperature. Any measurable change that it can cause in a substance can be used to measure temperature. Anytime I heat a wire, anytime I heat a metal, the resistance is something that is called the resistance of a wire. It is the resistance that is given to the flow of electricity through that material. Anytime I heat a wire, the resistance of that wire can change. So I can measure and the resistance is a measurable quantity. I can measure the resistance of the wire and use it to get the temperature of the object. And anytime that we have, anytime we heat a liquid substance, not just liquid substance, even gases, but liquid is more appropriate. Anytime we heat liquid substances, there's an expansion, it expands. And once it expands, I can measure that expansion in terms of the change that is happening to its volume, and I can adapt that to be used as in the measurement of temperature. So any measurable change that it can cause in a substance can be used to measure the temperature of a substance. That's why we have so many types of thermometers, because each of them are designed from our knowledge of a measurable change that is taking place due to the effect of heat on that object. But basically, I'm going to list out common types of thermometers that we have. There's one that is called liquid in glass. There's another thermometer that is called a resistance thermometer. There is another thermometer that is called a constant volume gas thermometer. Constant volume gas thermometer, or we just simply refer to it as gas thermometer. There's another type of thermometer that is called a thermocouple. Another name for a thermocouple is a thermoelectric thermometer. There's a thermoelectric thermometer. There are more. We can have what is called a bimetallic thermometer. So some examining bodies do not accept bimetallic thermometer as a type of thermometer. But we have liquid in glass, we have resistance thermometer, we have constant volume gas thermometer, and we have thermocouple. Thermocouple, like I said, is also called thermoelectric thermometer. When you learn a thermometer, it is necessary for you to know certain things about each of them. These are thermometers. When you learn a thermometer, it is necessary for you to learn what we call the thermometric substance of each of the thermometer. The thermometric substance. The thermometric substance in a thermometer is a substance that allows the measurement of temperature within the thermometer. It's a substance that enables the measurement of temperature within the thermometer. For liquid in glass, there's a particular liquid that is inside the glass whose expansion helps us to measure the temperature. The liquid can either be mercury or alcohol. For resistance thermometer, we just simply use a wire. It can be a platinum wire, or any other metallic wire. Constant volume gas thermometer, we use, of course, any gas or generally air. For thermocouple thermometer, we use two dissimilar metals, two metals that are not the same. Two dissimilar metals. Usually we can use copper and constantine. We can also have any other metals that once we have two dissimilar metals, two metals that are not the same thing, they form the thermometric substance. Now, we want to look at another parameter in a thermometer that we call the thermometric property. Thermometric property, I told you earlier that any measurable change that it can create in a substance can be used to measure the temperature of, Now, the property of these substances that change with temperature that cannot be used to measure the temperature is what is called the thermometric property. For example, liquid in glass, we said we use mercury and alcohol. What is the property in mercury and alcohol that allows us to measure temperature? It is the change in volume due to expansion. The change in volume with temperature. We understand that when we add heat to increase the temperature of this substance, they expand in a linear form. The expansion that takes place to this substance, anytime you add heat to them, is linear, is directly related to the change in temperature. As you increase the temperature, there's an increase in the expansion. As you increase the temperature, there's an increase in the expansion. So I can get the expansion, I can measure the expansion, and then use that to measure the temperature. Platinum wire, it is the resistance of the wire. The resistance of the wire. The change in the resistance of the wire. We understand that when we add heat to a wire, there will be a change in the resistance, and the resistance changes linearly with temperature. The constant volume gas thermometer. The constant volume gas thermometer is the change in the pressure of a gas. The change in gas pressure at constant volume. That's why it is called constant volume gas thermometer. Volume with temperature. Why do we need to ensure that the volume is constant? Because generally gases have three properties. They have pressure, they have volume, they have temperature. If I am going to measure the relationship between the pressure and temperature, I must ensure that the third property is kept constant. So the change in the pressure with temperature is something that I can use to measure the temperature in a constant volume gas thermometer. Thermocouple. Thermocouple is a change in the electric potential difference. Is a change in the electric potential difference between the junctions of the metals with temperature. And that is the electric property. We are still going to see that by the time I discuss thermocouple with you. So basically, these are the thermometers that we have. These are the substances in those thermometers that enables the measurement of temperature. And these are the properties of those substances that allow us, that we measure, and we now find a way to convert them to temperature values. So these are the various types of thermometers that we are going to be looking at now. We'll start with a liquid in glass thermometer. In liquid in glass thermometer, we simply have a glass that is made into a spherical bulb, and the spherical bulb leads to a narrow stem. Of course, there's now a thicker stem that is covering the narrow stem. This narrow stem will be called the bore. This will just be called the glass stem. And this will be called the bulb. So this is how a liquid in glass looks like. They will find a way to get liquid into this bulb up to a certain mark. It is believed, therefore, that if we expose the mercury in the bulb, if we expose this bulb to any hot surrounding, it will move into the mercury. The mercury will expand due to the heat, and it will move along the bore to the point for which the new temperature can now be determined. So this is how a liquid in glass thermometer looks like. These are just the three features of the liquid in glass thermometer. But why are they necessary, and what are the important things to note about it? Number one, the bulb must be made of thin glass. The bulb must be made of thin glass. Very thin. So thin, if you hold it too tightly, it can break. And why is that necessary? Because glass itself is an insulator. When we say it's an insulator, it is a material that does not readily allow the flow of heat through it. So if it becomes too thick, if the bulb becomes too thick, it takes a long period of time before the heat that we are trying to measure will get into the mercury inside the bulb. So you now create a thermometer that is going to take too long to measure the body temperature. You have a thermometer that is going to have a very long response time, and that is not good for a thermometer. Apart from even having long response time, it is possible that it is not all of the heat that will eventually get to the thermometer, to the mercury inside the glass. That way, we are going to have what is called a loss of heat, and there will be an inaccurate measurement of the thermometer, as in this case. So to ensure that this does not take place, we make sure that the bulb of the thermometer is as thin as it can get. So yes, that has accounted for the fact that, yes, we understand that glass is an insulator, but because it has now been made thin, it is still possible for us to get the heat across the thermometer into the mercury within a shorter period of time. And we will have a thermometer that will respond quickly to the measurement of temperature because the heat is getting to the mercury on time, and the mercury is going to immediately respond by expanding. Now, the bore is another thing that we should talk about. The bore must be very narrow. The bore must be very narrow because the expansion we are expecting is actually very, very small. You see from our class on expansion that most of the time, if there's going to be a change in volume, it is not something that is so large enough to even be seen. Most of the time, if you have an 100 centimeter cube of liquid, after going through a temperature difference of as high as 100, you can just, it could have expanded from 100 to 100.2. So it means a wide change in temperature of 100 was only able to create a 0.2 difference in a liquid volume of as much as 100. So generally, expansion values are very, very low. So if we are going to make them seen at all, then the bore must be as narrow as possible, Let me ask you this. If we make two different types of thermometer, of course, equal size of the bore are the same. But why the bore here is very wide, that means it has a large cross-sectional area. The bore here is very, very narrow. Being narrow means that if I have the mercury and the same amount of mercury in the bore, if I heat the two of them through the same change in temperature, in which of these do you think I'm going to have a larger difference? Of course, if the two of them expand by 0.2, let's assume that the two of them expand by a volume of 0.2 centimeter cube, I will see that 0.2 taking a longer length, going through a longer length in this than in this, because here the area is big. If the area is wide, remember that the volume is the area multiplied by the height. It means that if I am going to get a very good height, I must make sure that the area is as small as possible. And height is what we are measuring. We want our liquid to go as far as possible inside the bore. That can only be done if the bore is made thinner. In practical thermometers that you use in school or even in industry, you will see that the bore is so narrow that most of the time we even require magnifying glasses or lens to be able to see them clearly. And that is the purpose of the stem. Usually the stem is the only part of that thermometer that is made with thick glass. The thicker the glass, the more magnifying it becomes. It means if it is made of thin glass, it can magnify the reading on this very thin stem. Thicker glasses are good for magnification. So it can magnify the size of this narrow bore so that we'll be able to see whatever reading or whatever movement the liquid within the bore is having. So the essential features of a liquid in glass are the bulb. I said the bulb must be made of thin glass to help the responsiveness of the thermometer. The bore must be made as narrow as possible so that a small change in temperature will create an expansion that will still travel through a larger distance and will be easily seen for us to understand that the temperature has changed. And the stem must be thick because it will serve, one, to protect the bore, and two, to magnify the reading on the bore. Of course, it is the stem that will carry the reading. The stem has graduations on it to show the temperature at every point that the mercury inside the bore gets to. There are two different properties that we must know about a liquid in glass thermometer. There are two different properties that a liquid in glass thermometer all thermometer generally must also have. If we are talking about, number one, sensitivity. And number 2, responsiveness. The responsiveness. The sensitivity of a thermometer is the ability to detect a small change in temperature. The sensitivity of a thermometer is the ability of the thermometer to detect a small change in temperature, while the responsiveness of a thermometer is its ability to measure the temperature of its surrounding very quickly. If a thermometer is responsive, it means it has the capacity to get the measurement of, to detect the measurement of temperature as quickly as possible. If a thermometer is sensitive, it means if the temperature changes by the slightest amount, the thermometer will be able to detect it. For example, if I have a thermometer that is graduated in 10, 20, 30, 40, 50, 60, and 70. Then I have another thermometer that is graduated in 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. It clearly means that this thermometer is more sensitive than this, because if I expose the thermometer to a temperature of, let's say, 5, we expect the mercury level, the mercury thread, to get to this point. Now, if the temperature increases from 5 to, let's say, 5.5, this thermometer will still be able to show us by moving its mercury thread to somewhere between 5 and 6. We'll be able to know that the thermometer has increased by the slightest bit, 5 to 5.5. But let us check this thermometer. Let us assume that this is 0. If this thermometer is exposed to a temperature of 5, 5 will be somewhere around 10. If the temperature suddenly increased from 5 to 5.5, it will be so hard for this thermometer to show it, because the space available between 5 and 10 is actually very small. It might even have increased, but we will not be able to detect it because it is not showing a wide change for a small change in temperature. It's not showing a wide change in the length of the mercury thread for a small change in temperature. And one of the things that we can use to ensure that the thermometer becomes more sensitive is to reduce the size of the bore as much as we can. The narrower the bore, the more sensitive the thermometer will become. When the bore becomes very narrow, it will be able to produce a large change in the thread or the level of the mercury for a small change in temperature. So note that responsiveness of a thermometer is the ability of the thermometer to measure the temperature of a surrounding quickly. I explained how you can achieve responsiveness when I was talking about the bulb. The thinner the glass that you are using to make the bulb, the better or the more responsive the thermometer will be. So if the glass of the bulb is thin as possible, then it becomes very, 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 very responsive. There are other things that we can do in our thermometer to ensure sensitivity and responsiveness. We are still going to get to those ones. Now, we'll move into the comparison of the two liquids that I said can be used in a liquid in glass thermometer. We said earlier that in a liquid in glass thermometer, the thermometric substance can either be mercury or alcohol. Mercury or alcohol. Now, each of these two has advantages and each of these two also has disadvantages. So we are only going to pick the right one for the purpose that we need to use it for. There are alcohol in glass thermometers and there are mercury in glass thermometers, depending on, number one, the region that we want to use it, and number two, the purpose for which we want to use it. Now, we are going to try to look at what are the advantages of alcohol, of using mercury in our liquid in glass, and what are the advantages of using alcohol in our liquid in glass. Mercury's advantage, number one, stems from its boiling point. Mercury boils at 357 degrees Celsius. That means it remains liquid up to 357. So mercury can therefore be used to measure very high temperature. When they ask you for advantage, it is not enough to just say that mercury boils at 357. No, you have to, that is just a feature. You have to tell us how that feature has translated into an advantage for mercury. Because it boils at 357, it means that it can be used to measure very high temperature. If I want to design a thermometer that can measure up to 100, 200, 300 degrees Celsius, even up to 350, I can use mercury because I'm so sure that up until that range of temperature, it is still a liquid. An advantage for mercury is a clear disadvantage for alcohol. Similarly, an advantage for alcohol is a clear disadvantage for mercury. For example, I talked about the boiling point being an advantage of mercury. It is a disadvantage for alcohol. Alcohol boils at 78 degrees Celsius. That means you cannot use an alcohol in glass thermometer to measure anything whose temperature is beyond 78. You cannot even use an alcohol in glass thermometer to measure the temperature of boiling water, because at 100, that 100 water is expected to boil, alcohol will have vaporized, because generally liquids vaporize beyond their boiling point. So at 100 degrees Celsius, alcohol will have vaporized. So a boiling point is a disadvantage, clear disadvantage for alcohol. But melting point is not so. Alcohol melts or freezes at minus 115 degrees Celsius. Alcohol freezes at minus 115 degrees Celsius. That means alcohol will not become solid. When you're talking about a liquid, we need to look at the range for which it still exists as a liquid. So we are going to look at the upper limit beyond which it will cross to a gas, and we are going to look at the lower limit beyond which it turns to a solid. The liquid is only useful for us in this thermometer. That's why we call it a liquid thermometer, within the range that it exists as a liquid. Alcohol, for example, turns to solid at minus 115 degrees Celsius. So it means that alcohol can be used to measure very low temperature. Alcohol can be used to measure very low. If I need to measure temperatures like minus 10, minus 50, minus 70, minus 90, minus 100, minus 110, I will use an alcohol in glass thermometer, because alcohol freezing point is still down, minus 115. So where you have a prevailing low temperature to measure or deal with, alcohol in glass is always preferred. Mercury, however, freezes at minus 39 degrees Celsius. That means you cannot use mercury for temperatures that are below minus 39. Mercury freezes at minus 39, so it is a disadvantage. It cannot measure as low a temperature as alcohol can measure. Now we move on. Conductivity is another thing that can use to distinguish between the two. When the two of them accept heat, that heat will manifest itself earlier or quicker in mercury than alcohol, because mercury is a metal. Mercury is a metal. Being a metal, it means it will have an immediate effect in it. It will create an immediate expansion in it. That is not the case for alcohol. Alcohol is a non-metal. It takes a short period of time before the heat can manifest itself inside alcohol. So when you expose the two of them, to heat, mercury responds to that heat quicker, faster than alcohol. That means that mercury has a very good conductivity, and alcohol has a poor conductivity. Conductivity, therefore, is an advantage for mercury. It is a disadvantage for alcohol. Now, expansion. When you expose the two of them to heat again, alcohol expands more than mercury. Alcohol expands more than mercury. The meaning of that is that if mercury expands by a certain amount, alcohol will expand by an amount that is greater than that of mercury. We will say that it's even given in literature that alcohol expands 6 times. The expansion of alcohol is 6 times greater than that of mercury. So please do not mix the expansion or the expansivity with conductivity. Conductivity helps us to understand the which of the substance expand faster or expand first. Expansivity helps us to understand which of the substance expand more. While mercury expands first, it expands faster than alcohol. Alcohol, by the time it starts to expand, though is slower in its response to heat, but by the time it starts to respond to heat, it will expand more than mercury. So mercury expands first, but alcohol expands more. And there are other things that we can talk about. Mercury, for example, is colored. It has a silvery color. So when you put mercury inside glass, it can easily be seen because it is colored. Alcohol is not that good. Alcohol is colorless. Alcohol is just like water. Pure alcohol is just like water. That means that when you put alcohol inside glass, it's like putting water inside glass. It's minuscule. Its movements are not so clear to see, except you now color it. There are other differences too. Alcohol wets glass. That's a disadvantage for alcohol. Alcohol wets glass. You know when you put water inside a glass cup and you throw it away, you will still find drops of or droplets of water around the walls of the glass. That is an example of a liquid that wets glass. Alcohol does that too. Mercury does not wet glass because its molecules do not have strong affinity for glass molecule, glass molecule, sorry. So because of that, it can not wet glass. Not wetting glass is an advantage for mercury. It is a disadvantage for alcohol. The meaning is when mercury expands, by the time its temperature drops, the whole of the mercury within the ball will also move down. That helps mercury to expand uniformly and to contrast also uniformly. So it will also help in the accurate measurement of temperature. So in adding to what I said earlier about the properties of a thermometer, I said thermometer has two properties. Thermometer can be responsive, the responsiveness of a thermometer, and the sensitivity of a thermometer. Responsiveness has to do with the need of the thermometer to measure the temperature of the surrounding very quickly. If I want to design a thermometer with either mercury or alcohol that will have a great responsiveness, that will measure the temperature of my surrounding quickly, then I must use mercury. Because I said it earlier, because mercury is a metal, it has a strong conductivity. Having a strong conductivity means it will almost immediately manifest itself inside it. Being that, it means that if I use mercury to make a liquid in glass thermometer, once the heat gets to the mercury expands to show me my temperature immediately. So if you need to design a thermometer that is responsive, it clearly means that I must use mercury. But alcohol, on the other hand, is preferred in situations where we want to design a thermometer that has very good sensitivity. Sensitivity is the ability of the thermometer to dictate slight change in temperature, so that once you change the temperature by the slightest amount, it will be visible. The movement of the thread of mercury within it will be visible. Imagine if you have a thermometer, I said it earlier, that can give you a wide change. For a small change in temperature, then that is good. And because alcohol has greater expansivity, alcohol expands 6 times more than mercury. It means if I use alcohol inside my thermometer, a slight addition of heat to alcohol will give a wide change in its volume because of its higher expansivity. So alcohol is preferred for sensitivity, while mercury is preferred for conductivity. We move on with that. There are now that we know how a liquid in glass looks like, we need to move to the types of liquid in glass that we have. We have what I will call a laboratory thermometer, the normal liquid in glass that is used for scientific purposes in the laboratory. Then we have what is called the clinical thermometer, that is usually used in clinics and hospitals, clinical thermometer. And we have what is called the maximum and minimum thermometer. The maximum and minimum thermometer. Sometimes maximum and minimum thermometer can be referred to as the 6 thermometer, the 6 thermometer in reference to the scientist that first gave it to us. Now we have a laboratory thermometer, we have a clinical thermometer, we have a maximum and minimum thermometer. We are still going to go into detail on each one of them, but for now, let us look at how to calibrate a thermometer. Let us say that I've just made a new thermometer and I need to calibrate it. I need to put the mark so that I will know at any point what the temperature at each point is. If I need to do that, the very first thing I must get, it is necessary for you in the process of calibrating a thermometer to at least get 2 fixed points. If I know 2 fixed points on the thermometer, then I can know where all other points are. I can know where I can put all other temperature values on the thermometer. Usually, the 2 fixed points that we always use are called the upper fixed point and the lower fixed point. Though in new thermometers, there are other points that we can also find in them as fixed points. But generally, a thermometer will have lower fixed point and the upper fixed point. The lower fixed point of a thermometer is the temperature of pure melting ice at standard atmospheric pressure. Is the temperature of pure melting ice at standard atmospheric pressure. That means that the temperature of lower fixed point of a thermometer is 0 degrees Celsius. Because if you have pure ice that is melting, if you have pure melting ice at normal atmospheric pressure, ice melts at 0 degrees Celsius. Ice melts at 0 degrees Celsius, or water freezes to ice also at 0 degrees Celsius. That temperature is regarded as the lower fixed point of a thermometer. Please, if you ask to define it, you must put the word pure, because once it is not pure, water will not melt, or water will not freeze, or ice will not melt at 0. And it must be at the normal atmospheric pressure, because prevailing pressure and purity are 2 things that can affect both the melting point and the melting point and the boiling point of substances. Upper fixed point, on the other hand, is the temperature of boiling water at 1 atmospheric pressure, at standard atmospheric pressure or 1 atmospheric pressure. The temperature of boiling water at 1 atmospheric pressure. You can also put the temperature of pure boiling water at normal atmospheric pressure. Of course, I said purity and pressure are 2 things that affect both the boiling point and the melting point. So if you want to refer to them, you must ensure that you put, for example, we said water boils at 100. Water does not always boil at 100. We are going to see that very soon. Water can actually boil at any temperature. If I can change the prevailing atmospheric pressure, it is possible for me to make water boil at temperatures that are even as low as 50, 40, 30 degrees Celsius. So if you are going to refer to 100 as the boiling point of water, it is because the atmospheric pressure is 1, is normal, the way we have it now, and the water is pure. So upper fixed point is the temperature of pure boiling water at 1 atmospheric pressure or standard atmospheric pressure. So 100 degrees Celsius. The difference between the fixed points of a thermometer is called the fundamental interval of a thermometer. The difference between the fixed points of a thermometer is called the fundamental interval. So that is measured on a liquid in glass as length. The fundamental interval is measured on a liquid in glass thermometer as length. Now, how do we get the upper fixed point and the lower fixed point of a thermometer, of a new thermometer? What we just need to do is we'll get the thermometer, we'll put it in what I call pure melting ice shavings inside a funnel. Melting ice shavings is ice that has been broken down into tiny, tiny, tiny pieces. Ice that has been broken down into tiny, 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 tiny pieces. Ice that has been broken down into tiny, tiny pieces. Of course, we have to put that on a vessel that will serve as a container. So if the ice starts to melt, we can be so sure that the temperature at that time is 0 degrees Celsius. It has to be melting ice shaving so that it will have proper contact with the bulb of the thermometer. We need it to have proper contact with the bulb of the thermometer. If the ice pieces that you are using are too big, then what you are going to have is much of spaces around the bulb. Now we need proper contact between the bulb and the ice. So once the ice starts to melt, we'll understand that the prevailing temperature at that time is 0 degrees Celsius. So we expect the mercury inside our new thermometer to contrast until it gets to a particular point. Once it contrasts and stays at a point steady, then we mark that point with any sharp material. Don't break the glass anyway. I will call that the lower fixed point of our thermometer. In getting the upper fixed point of the thermometer, you remove it. You put it in a device that is known as the hypsometer. Hypsometer is just a container with boiling water. Of course, there's a vent to ensure that there's no buildup of excessive pressure inside the device. This is water. Once you heat the water and the water starts to boil, we expect vapor to come out of the water and stay around the bulb of our thermometer. There is going to be a manometer. We are going to see that very soon under gas law. There's going to be a manometer to ensure that the pressure within the device is the same as the atmospheric pressure, to show us that the pressure is still within the atmospheric pressure. In drawing your manometer, you must ensure that the level of mercury in the manometer, the two levels are the same. If the level of one is more than that of the other, what you are indirectly telling us is that there's an inequality between the pressure of the container and the surrounding. And in that case, you are not going to get the exact upper fixed point that you want. So you must ensure that in drawing this is also the same. So you allow this process to go on for a while, through which the mercury level is expected to expand, and stays at a point. Once it stays at a point, we agree that that point is the point where it is measuring 100 degrees Celsius, the temperature of boiling water at standard or normal atmospheric pressure. So we'll mark that with a pin and we'll refer to it as 100 degrees Celsius or the upper fixed point. So that is how we get the two fixed points in a thermometer. Now that we know the fixed point in a thermometer, we can now decide to calibrate evenly or uniformly the other point. If, for example, this point is my upper fixed point, that's the point where the thermometer will get to for me to read the temperature as 100. If this is my lower fixed point, this is where the mercury level will get to for me to read it at 0. So if I know this, I can now take my ruler or any standard lineal device to mark other points into what they will give me. And clearly, I will have a thermometer that has been fully and well calibrated. There are also formulas that we can use to know, so that if I know the length from the bottom of the upper fixed point, and I know the length from the of the lower fixed point, and I know the length from the bottom of the upper fixed point, then I can find the temperature at any length that you give to me from the bottom. If, for example, the length from the bottom of the lower fixed point is 5 centimeters, the length from the bottom of the upper fixed point is 50 centimeters, I can be asked to find the length from the bottom of a point that is at 6 or 16 centimeters. That should be very easy for me to know. What I will do is I'll use the extrapolation formula, something that is already very common in our textbook. I'll call the points that I want to find the temperature of, I'll call its temperature theta. Let me use a more generalized form. Instead of using 5 centimeter, let us assume that the length of our lower fixed point is L0. The length at 0. Let us assume also that the length of our upper fixed point is L100. That is length at 100. So the length where where the question wants me to find the temperature, let me call it L theta. So L theta corresponds to theta the way L0 corresponds to 0 and L100 corresponds to 100. I can now set out to use this formula. I can say that L theta minus L0 all over L100 minus L0. I have subtracted both L theta and L100 from L0, which is my lower fixed point. I have subtracted my lower fixed point first from the upper fixed point. What I have as a denominator here is the fundamental interval, the difference between the upper fixed point and the lower fixed point. That same lower fixed point, I will now subtract it from L theta. So the way I've arranged the length, I will now also arrange the temperature like that. It means this should be the ratio of the difference between their length must also be equal to the ratio of the difference between their temperature. So this must be equal to theta minus 0 all over 100 minus 0. Theta minus 0 all over 100 minus 0. And this will give us the formula that I want to use, that I need to use. If I am going to use this formula, clearly, it simply means that if I want to use it to solve the illustration that I gave earlier, L theta, let us assume is 16, L0, let us assume is 5, L100, let us assume that it is 50. I can simply put 16 here, 0 here, 5, 0 here too, no. L theta is 16, let me solve it. L0 is 5, L100 is 50, and L0 is also 5. Then I can turn that into theta minus 0 is already theta, 100 minus 0 is already 100. So mind you, if I solve this, I will be able to get my theta. We are still going to see more examples to solve this question from our next section. Now, please understand that I have arranged the length the same way I've arranged the temperature. But if I need to bring that and make it smaller, where I have theta, L theta, I have theta, the corresponding position of my L0 is 0, the corresponding position of my L100 is 100, the corresponding temperature that is in my L0 is 0. So I can also now contrast that into L theta minus L0 all over L100 minus L0 is equal to theta minus 0 is 0, is theta, all over 100 minus 0 is 100. So that should be the formula that we are going to use for this part. So we'll move on to a discussion on the types of thermometer that I said we've had, that I said we can have, the types of linear and the types of liquid and glass thermometer that we can have. We are still going to come back to see this formula. We've talked about laboratory thermometer. We want to see clinical thermometer. Clinical thermometer is also a liquid in glass thermometer. It has essentially the same feature as a liquid in glass thermometer. In fact, it's just an example of a liquid in glass thermometer. So this is the bulb, the same bulb that I said should be made with thin glass. This is the bore. This is a stem. We are still going to talk about the stem. I said this is the bulb that contains the expanding liquid. Now, liquid in glass thermometer are used generally in hospital to determine the temperature of patients. Because we do not expect the temperature of a person to go beyond certain set level, there's a small range for which we need the liquid in glass thermometer. In fact, generally, most liquid in glass goes between 35 degrees Celsius, measures between 35 degrees Celsius to 43 degrees Celsius. Under no condition are we expecting the temperature of a person to be less than 35. And under no condition are we expecting the temperature of a living person to also be greater than 43. Generally, the average temperature of the normal human, I said earlier, is around 37 degrees Celsius. So 35 degrees Celsius, 43 degrees Celsius. So number one feature of a clinical thermometer is the small range for which it is expected to be used. It is only expected to be used between 35 to 43. A normal laboratory thermometer can measure temperature if, let us assume that a normal laboratory thermometer has between 0 to 100. In fact, we have some laboratory thermometer that has from minus 50 to about 330. Now, if that is the case, or even minus, let's say minus 30 to about 330, if that is the case, it means if I'm going to turn this to a liquid in glass thermometer, I only need the range of temperature that is from 35 to 43. In thermometers like this, because you have to accommodate lower values and higher values, then you will expect that the range of 43 to 50, 35 to 43 on this type of thermometer will be very, very small. Also, on thermometers like this that even have greater range, we expect that the difference between 35 and 43 will be so close, we may not even get to see the difference between them. So it is just this little range that we now need to expand upon to get a clinical thermometer. And what do? It means if we have to expand this, the bore within it must even be narrower, must be very narrow. If the bore of a normal laboratory thermometer is this wide, we expect the bore of a clinical thermometer to be so narrow, we may not even have the space to show the line between them. So why? Because we need to make the bore smaller so that we can create a longer space actually between the two temperature value range that we need to accommodate, which is still close. 35 to 43 is just a difference of 7. You can't compare it with something that is measuring from 100 to 0, or from 330 to minus 30. So one feature, therefore, of a clinical thermometer is the bore must be very narrow. In fact, we use the word fine bore. It must be narrower than narrow. So it must be very fine. So that will create problem, of course. Number one, the problem of the problem of visibility. Because the narrower it is, the more difficult it will be for us to see the movement of the mercury thread through it. So that the visibility, therefore, is assisted by the special stem that is used in this type of thermometer. It is not like the stem in all other types of thermometer. Yes, the stem in all other types of thermometer too must be thick. Here it must be thicker. And in some textbook, you will see that they even have it pear-shaped. They will say a pear-shaped stem. Pear-shaped. The reason why it has to be pear-shaped is to ensure, number one, a magnification of the reading in one direction, to ensure that the reading becomes bolder, particularly in a direction. So it makes it easier to see it. So whatever is done to the stem is for the purpose of easy visibility by magnification. Please don't forget. Now, another feature that we have here, which is one thing that completely set the clinical thermometer apart from every other liquid in glass thermometer, is this constriction along this narrow bore. There's a constriction along this bore. Why is that constriction? Why do we need it? When this liquid in glass thermometer is put around the body of a patient,
we expect that the mercury will expand past this constriction and get to a point where it is going to indicate the body temperature. Let's say the body temperature is 37.2. The body temperature is around 37.2. So when this is removed from the body, the thermometer stays at 37.2. Normally, when you remove a thermometer from an hot surrounding, the mercury will immediately start, the liquid in it will start to contrast. It will start to leave that particular point where you can read the temperature, and it will start to move down, because now it has left the hot surrounding. It has now gotten to a point that is having a temperature that is lower than where you have taken it from. So immediately it will start to also attempt to measure the temperature of where it is now, and the mercury will start to go down. But we need the mercury thread to remain at the point where the temperature can be seen for a long period of time, so that it will give the doctor or whoever is measuring your body temperature enough time to make the likely or the possible inferences from that temperature measurement. So the constriction enables the mercury thread to remain at the point of the maximum temperature of the body that has been measured without allowing it to go back into the bulb. In fact, it is until it has been measured and it has to be jigged, it has to be shaken before you can take this back into the bulb. If that is not done, it remains at the point of measuring the maximum temperature for a long period of time. So that is the clinical thermometer, and that is the feature of a clinical thermometer. We move on to maximum and minimum thermometer. Before we move on, there's also another question that you can have on clinical thermometer, that how do we sterilize a liquid glass thermometer? Normally, we sterilize objects by putting them in hot water or lukewarm water, or hot water generally. But we cannot sterilize a clinical thermometer by putting it in lukewarm water. Why? Because we expect that it will attempt to measure the temperature of the hot water. And if it does that, remember that the temperature of hot water is 100. The maximum temperature that it is designed for is 43. If it attempts to measure 100, there will be an excessive expansion of that mercury beyond what this thermometer can take, and you can actually damage it. So how do we now sterilize it? We put it in a solution, we wash it in a solution of detergent, and then we rinse it in lukewarm water whose temperature is not as high as 43. We now move on to the 6 maximum and minimum thermometer. This is how the combined maximum and minimum thermometer looks like. It is the only thermometer that makes use of 2 different liquids. It's the only thermometer that makes use of 2 different liquids. The liquid that is presently being shown is mercury, while the other liquid atop the level of mercury in both arms is alcohol. So we have alcohol and we have mercury. So we have also alcohol vapor on this other part. This is alcohol vapor or air. You can have air here or alcohol vapor. But this end is completely filled with alcohol. The 2 of them are immiscible, so it is possible for us to have an arrangement where they do not mix. There are 2 steel indices. One index, the 2 of them indices, 2 small steel indices directly placed atop the meniscus of mercury, directly placed across the meniscus of the mercury. They are tight enough to stay in position, and they are loose enough for them to be moved up and down by the mercury meniscus. They can be moved up and down by the level of the mercury, but they are also tight enough to stay at positions wherever they are. We call them steel indexes. Index for 1,
Now, this is the 6's maximum and minimum thermometer. How does it work? What does it do? It is used to determine the maximum and minimum temperature over an extended period of time. If today, it could be for a day, it could be for a month, for a week, for a whole year. If today, for example, I want to find the maximum and minimum temperature, knowing fully well that the temperature values from the morning down to the evening will have gone through different values. I'll now want to find, of all of those values, which one has been the minimum for the day and which one has been the maximum for the day. I will just set this maximum and minimum thermometer outside or anywhere, and I will come back to it. I'll set it at the point at the start of the observation period, and I'll come back to it at the end of the observation period to see what has been the maximum and minimum temperature that was recorded for that particular day. If for a whole week, I'll set it at the start of the week. I'll come back to it at the end of the week to also check what has been the maximum and the minimum temperature for the whole week. Now, if I need to do this, very simple. When you leave a maximum and minimum thermometer, when you leave it down, one thing that you know is the two of them will be exposed to it, both mercury and alcohol. So the alcohol will expand. Mercury will also expand. Alcohol expands, mercury expands. But there's something I discussed earlier, that the expansion of alcohol is far more than the expansion of mercury. The expansion of alcohol is 6 times that of mercury. If mercury expands by 1 centimeter cube, same volume of alcohol will expand by 6 centimeter cube. Now, if alcohol expands, the mercury will also expand. So what will have taken place here is, because alcohol expands on this arm, it will try to create space for itself. And how will it do that? It will push down the mercury on this arm, and then the mercury on this other arm will be pushed up. Don't worry, there's still space for the alcohol here to expand to. So the mercury here can actually push up the alcohol level for as long as the expansion of this alcohol can take. So as the alcohol expands, it pushes down mercury on this arm. I can call this arm A, and this arm B. It pushes down alcohol on arm A, then the alcohol on arm B will go up. As the alcohol on B moves up, it will move up the Still index. It will gradually move up the Still index. Let us assume that the Still index is here. If the expansion is now greater than what we have recorded, because the temperature has also increased, we expect a greater expansion due to an increase in that temperature. So that will further lead to a greater downward movement of mercury along this arm and an upward movement of mercury along this arm. So it's now possible that due to the expansion of mercury, the Still index on this arm is continuously moved up by the meniscus of alcohol, by the meniscus of mercury, sorry. When the temperature reduces, the reverse will take place. So when the reverse takes place, we expect, reverse now means a reduction in temperature. When there's a reduction in temperature, we expect contraction. Alcohol on this arm will contrast, mercury will also contrast, but alcohol here too will contrast. It is the alcohol that you have on this arm that is going to dictate the movement process of the 3 columns of liquid that we have. If the alcohol in this arm contrasts, while the other time when you increase the temperature, it will expand, so push down this mercury, and this mercury will also push down the alcohol and the Still index on this arm. But when it contrasts means it will reduce the space available. When it does that, the space available for it reduces, then the mercury here will move up. The mercury here will move up. And as the mercury here moves up, it pushes the Still index upward. It also pushes the Still index upward to measure lower temperature. So along this term, you have this term graduated in lower temperature, because the smaller the temperature, the more will be the movement of the mercury on this arm due to the contraction of alcohol. So it is possible for you to have temperatures like 30 degrees Celsius,
20 degrees Celsius, 10 degrees Celsius is 0 degrees Celsius, minus 10 degrees Celsius, minus 20, minus 30 degrees Celsius. But along this arm, because this is the arm to which you have to push the steel index when the temperature is increasing, you have an increasing temperature due to the upward movement of the mercury on this arm. So the temperature here can be minus 10, 0, 10, 20, 30, 40, and so on and so forth. So at the end of the whole process, when you come back to meet your maximum and minimum thermometer, you are not going to necessarily use the level of mercury or alcohol at any point. It is possible that you now get to meet the steel index at this point on this arm and at this point on this arm. The mercury level could even be at, let's say, 10, and the steel index can be at 30. The mercury level here could be at maybe 10 also, and the steel index here can be at maybe 15. What we are saying in essence is that it is possible for, okay, let us say here it could be at, because there's a reduction on this arm, let us say here it is at 20. What we are saying in essence is at a point during the day, the mercury on this arm went as high as driving the steel index to this particular point where the temperature was 15. It means at a point during that particular period of observation, the lowest temperature recorded was 15 degrees Celsius. And at a point during that particular point of evaluation, the highest temperature was 30 degrees Celsius. Highest temperature was 30 degrees Celsius. Yes, of course, when you came back, you met the mercury level at 20, and you met the mercury level here also at 20. It means that is the temperature as of now. But during the day, the temperature grew. At one point during the day, the temperature grew as high as getting to 30. And during that same day, the temperature was as low as getting to 15. That was why you met the steel index here. So when you come back at the end of the period of observation, all you just need to check is come back, check the point where the steel indices are, and that will give you what is the lowest temperature for the day and the highest temperature for the day. And that is basically how a maximum and minimum thermometer works. Of course, if you now have to use it for another day, you have to find a way to get back the steel index to the surface of the mercury. That question has also been asked before. I think the material that we always use to reset the steel indices back to the top of the mercury, so that we can now start to use it for another, the observation for another period of time, is magnet. Once you just scrape a magnet around the side of the glass, the magnet will draw down the steel index, it will draw down the other steel index and bring them back to the top of the mercury, so that you can now use it for another set of observation. So that is how a maximum and minimum thermometer basically works. And those are the three liquid in glass thermometer that we have. We'll take some questions on liquid in glass thermometer at this point. I will try to see what we'll still have to learn from them. It is necessary for you to also understand that we are coming back to other types of thermometer. Question 1. We are asked to state 4 properties of a liquid which makes it suitable for a thermometer to be used in a school laboratory, and explain why each property is desirable. Number 1 is that the liquid must have uniform expansion, must experience uniform expansion, must expand uniformly with temperature. The liquid must expand uniformly with temperature. Any liquid that does not expand uniformly with temperature cannot be used in a thermometer. It means the difference is going to, because the scale of a thermometer must be linear. The difference in length from 0 to 1 must be the same thing as difference in length from 1 to 2 must be the same thing as difference in length from 2 to 3. If a thermometer is uniform, that can easily be. If the expansion of a
liquid is uniform, that can easily be achieved. Where that is not uniform, that cannot be achieved. In fact, that is the major reason why we do not use water and in a thermometer. Water will have been easily preferred. Why? Because it is the safest and the cheapest liquid that anybody can get. But we don't use water because water does not have a linear or uniform expansion with temperature. Water has experience what is called anomalous expansion. Between 0 to 4, water does not expand. When you take water at 0, if you heat it, it will not expand. Instead, it will do the opposite. It will contrast. When it contrasts, it keeps contrasting until its temperature becomes 4 degrees Celsius. It is when it gets to 4 that it will start to behave like a normal liquid. So the expansion of water is erratic. So before we can use a liquid, it must have uniform expansion so that it can give us a uniform scale on our thermometer. Another property that we can talk about is that the liquid must not wet glass. The liquid must not wet glass. If it is a liquid that wets glass, it cannot be used in a thermometer. The liquid must be opaque. The liquid must be opaque means the liquid must have color so that it can easily be seen. It is only when it is opaque that it must easily be seen. If we have to use a liquid that is not opaque, then we must get it colored by adding certain dye that will not affect its other physical properties that we need. The liquid must have high boiling point and low melting point. It must have high boiling point and low melting point. It must have, we will say that it must have a wide useful range. A liquid that melts at maybe 10 and boils at 50 can only be used between 10 and 50. So the liquid must have a wide useful range so that it can use it to make a thermometer that can measure a wide range of temperature. Any of those things are things that we can talk about. The liquid must also have good conductivity so that it can measure the temperature of its surrounding, so that the thermometer it is used to design can measure the temperature of its surrounding quickly. The liquid must have good expansivity, high expansivity, so that it can improve the sensitivity of the thermometer. So that is the answer to the question that we have at hand. There's another question that we should check still under liquid in glass thermometer. We are told that an uncalibrated liquid in glass thermometer was used in determining a Celsius temperature. The readings are tabulated below. We are asked to determine the value of L in the table. The table looks like we have temperature in degrees Celsius. It's divided into 3 columns for values. Then we have the length of the column. Then we have -6 is 0, 100, -6 degrees Celsius is 0 degrees Celsius, 100 degrees Celsius. And then we have L 2.0, 15.0, L 2.0, and 15.0. Those are the things that we have. We are asked to now find the value of L. So what we'll simply use is the formula that I gave you under calibration of a thermometer, the extrapolation formula. We can use, remember it is L theta minus L0 all over L100 minus L0 is equal to theta minus 0 all over 100 minus 0. So if we decide to put in the values that we have, the theta in this case has been given. Theta is the temperature, the other temperature that you are given apart from the lower fixed point and the upper fixed point. The lower fixed point and the upper fixed point, any other temperature that you are given outside those two becomes your theta. So the theta in this case is our -6. So our L at theta has not been given. The length at theta has not been given. The length at 0 has been given to be 2.0, and the length at 100 has been given to be 15.0 in centimeters. This is in centimeters. So we can put in the values. If we do that, we have L at theta, L minus L at 0 is 2, L at 100 is 15, and L at 0 is also 2.
that should be equal to, our theta is minus 6, please. It is not 6, it's minus 6 all over 100. We continue the evaluation. That will be L minus 2 all over 13 is equal to minus 6 all over 100. If we cross multiply, that will be 100 bracket L minus 2 is equal to 13 times minus 6. So we have 100L minus 200 is equal to 13 times minus 6 is minus 78. So 100L must be equal to minus 78 plus 200. If we take 200 to the other side, we have 100L must be 122 degrees. So that should be L, which is 122, sorry, all over 100, and that must be 1.22 centimeters. That's our length. And that is the end of the question.
Here we are told that the scale of a mercury in glass thermometer is linear. The scale of a mercury in glass thermometer is linear. One of such thermometer has a scale that extends between minus 10 degrees Celsius and 110 degrees Celsius. It has a scale that extends between minus 10 degrees Celsius and 110 degrees Celsius. The length of the scale is 240 millimeters. There's a thermometer. It has a scale that extends between minus 10 and 110 degrees Celsius. The length of the scale starts from here and ends here. The length of the scale is 240 millimeters. We can continue. What is meant by the statement the scale is linear? If the scale is linear, it means a degree change in temperature gives a corresponding change in the length. A degree change in temperature, every degree change in temperature, every 1 degree change in temperature gives an equal change in temperature. An equal change in temperature. That is what it means that the scale is linear. If you go from minus 10 to minus 9, the difference that you are going to have will be the same thing as if you go from minus 9 to minus 8. The difference you are going to have in length will be from minus 8 also to minus 7. Every degree change in temperature gives an equal change in the length of the mercury thread. Now we move on. We are asked to now calculate the distance moved by the end of the mercury thread when the temperature of the thermometer rises from 0 to 1. When the length rises from 0 degrees Celsius to 1 degree Celsius, what will be the length that it will cover? And also from 1 to 100. From 1 to 100, when it goes from 1 to 100, what will be the length that it will also cover? What will be the length that it will also cover? Now, so we are also asked to find the sensitivity of a thermometer, but we do this first. We will observe that here we are not even giving 0, the lower fixed point. We are not giving 100, the upper fixed point. But we can easily use what I call proportionality in your mathematics to solve this problem. You don't need to use the extrapolation formula because you don't even know the lower fixed point, you don't know the upper fixed point. Now, if I want to use the extrapolation formula, what I will just do, if I want to use proportionality, I will look for this change in temperature. The change in temperature will be 110 minus 10, and that is 110 plus 10, and that should give me 120 degrees Celsius. So therefore, this thing is showing me that a change in temperature of 120 degrees Celsius is giving us a rise in mercury thread of 240 millimeters. So 120 degrees Celsius in temperature produces a change in length of 240 millimeters, or corresponds to a change in length of 240 millimeters. With that, I can now find what they want me to find. They want me to find what will be the length through which the mercury
thread will travel from going from 0 to 1, I will know that a change of 0 to 1 will give me a change of 1 degree Celsius. If I already know that 120 gave me a change of 240, what will 1 degree Celsius, that is 0 to 1, what will it give me? I can represent that with x, and I can decide to cross multiply, and I'll get my answer. If I do that, I will have 120x must be equal to 240. So that should be x must be equal to 240 divided by 120. If I divide that, I should have 2 millimeters. And that is the final answer to that. I can also use that to solve for 1 to 100. 1 to 100 will give me a temperature change of 100 minus 1, and a temperature change of 100 minus 1 is 99. So I can also use this. Now that I even know 1, it becomes very easy. 1 degree Celsius change in temperature will give me a change in length of 2 millimeters. If it will give me a change in length of 2 millimeters, I can therefore say that a 99 degrees Celsius change in temperature will give me y. If I cross multiply, y times 1 is y, must be equal to 2 times 99. 2 times 99 should give me 198 millimeters, and that is the answer that I have here. The next question wants me to find the sensitivity of this thermometer. The sensitivity of a thermometer, the sensitivity of a thermometer can be expressed as a quantity, and the formula that we are going to use to find it is the change in the thermometric property, the change in the thermometric property all over the corresponding change in temperature. The corresponding change in temperature. If that is the case, I can now just simply use any change in thermometric property. The thermometric property of a liquid in glass thermometer is the change in volume due to expansion of the liquid with temperature. But that change in volume is represented by length because it has uniform cross-sectional area. So I can just say that the change in length all over the change in temperature. I can use any of the values that I have here. For a 120 degree change in temperature, I recorded a change in 240 millimeters. For a 1 degree Celsius change in temperature, I recorded a change of 2 millimeters. I can even use that one directly. For a 99 degrees Celsius change in temperature, I recorded a change of 198. So I can use the value that was given to me, the change in the thermometric property. The thermometric substance rose by 240 millimeters when the temperature changed by 120 degrees Celsius. If we divide that, we should have 2 millimeters per degree Celsius. And that is how we find sensitivity. What this simply translates into is that for every 1 degree change in temperature, I will record a change in length of 2 millimeters. You are now the one that will determine if this is good enough for you as sensitivity of your thermometer. It means this type of thermometer I can even record easily and 0.5 degree change. If 1 degree change in temperature is giving me 2 millimeters, 0.5 degree change in temperature will give me 1 millimeters, and 5 degree change in temperature will give me 10 millimeters. So that is how to determine the sensitivity of a thermometer. Just divide the change in the thermometric property by the change in temperature, and you can use this for any type of thermometer that you have. So I think we'll put a stop to that for a liquid in glass thermometer. We'll quickly describe or discuss all other types of thermometer. I will try to look for questions to solve on each and every one of them. So other types of thermometer are constant volume gas thermometer, CVGT, constant volume gas thermometer. Constant volume gas thermometer uses the idea that anytime we increase the temperature of a gas, then the volume and the pressure of the gas will increase. If I decide to now keep the volume constant,
If I decide to keep the volume constant, that means that the effect of the change in temperature can now be seen in only the pressure. So I can measure the pressure of the gas at the prevailing temperature, and I can now use it to get the temperature that gave me that pressure. So what I simply do is I will have a vessel that contains a gas, or more commonly air. That vessel is connected by a narrow glass tube to a manometer that can be used to determine the temperature. Of course, we know that the manometer is a device that can be used to measure the temperature, that can be used to measure the pressure. You can refer to our class on gas law to see how that can be done. So this is the vessel that contains air, and this is the manometer. The manometer A, and this is the mercury in it. Call this point B. So this is how a constant volume gas thermometer looks like. And how does it work? We simply have to put this end into whatever it is that we want to find the temperature of. We have to put it into whatever we want to find the temperature of. We expect that when we heat this medium, the temperature, the heat from this medium will go into the air and expand air. When air takes the heat, it expands. It expands means that it will push down along this arm. It travels along this arm. Of course, the arm is already having air in it because nature does not allow vacuum. So we have air all through. But when you now heat, this expands. When it expands, the volume of air in the tube increases. So what that means is it can drive down. When it expands and the volume increases, it will drive down the mercury along this arm so that the mercury along this arm will go up. It will push down the mercury along this arm, so the mercury along this arm will go up. Now, if we don't want that to take place because we understand that we want to ensure that the gas remains at constant volume, what we simply have to do is to raise this end. If we raise the whole of the tube on this arm, if we raise it up, it is possible to get back the level of mercury to the same point where it is. If, for example, it was at this point, if due to the expansion of that gas, it was now forced to go down, way down. If it goes down on this arm, we expect that it will go up on this arm. If that is the case, by ensuring, if we want to ensure that it remains at constant volume, now it's not at constant volume, there's a change in the volume of the gas. That is why it has pushed down the level of mercury. If we now want to get it back to being at constant volume, all we just need to do is we hold this arm, raise it up. When we raise this arm up, the mercury along this arm will go back to A. It will go back to A. And at that point, we will know that we can say that it is now at constant volume. So the change that has happened to it has not affected its volume, or it has affected the volume, but we reduce it back to being, we ensure that it maintained the initial volume. So what we will now do is to measure the pressure change that, of course, will have happened. We'll measure the pressure change by now determining the difference in the height or level of the mercury in the two columns. So once we get that pressure, we can now use our extrapolation formula to also convert it back to temperature. And that is how a constant volume gas thermometer works. The constant volume gas thermometer is the most accurate of thermometers. In fact, it is used to calibrate every other type of thermometer. If a constant volume gas thermometer is used to measure the temperature of a medium, and we have a set value, let's say 30 degrees Celsius, we are so sure that the temperature of that medium is 30. Liquid in glass thermometer is not exactly accurate because of the expansion of the container, the vessel also. But constant volume gas thermometer is the most accurate thermometer. It has its own disadvantages anyway. Because of the large vessel that
will have to contain the air. It cannot be used to measure the temperature of small drops of water. If I want to measure temperature of small objects or tiny or so small amount of a liquid, I cannot use this to measure it, because before it can be used to measure the temperature of a substance, it must be completely immersed into that substance. And that is the disadvantage of constant volume gas thermometer. Now, the extrapolation formula that I will use to get the temperature that is shown to me by the constant volume gas thermometer, I will expose it to a temperature of 0, and I will measure the pressure that it is giving me at 0. I'll call it P0. I will expose the constant volume gas thermometer again to a pressure of 100, and I will measure the temperature is given to me, the pressure is given to me at that 100. I will call it P100. I will take those things as its upper fixed point and its lower fixed point and its upper fixed point. Now, if it is giving me any other temperature apart from what it gives me at 0 and 100, then it is definitely showing me another temperature. I will call that temperature theta. I can now find theta by writing the same expression that I wrote for the liquid in glass thermometer. This time I'm going to change the length to the pressure. So it becomes P theta minus P0 all over P100 minus P0. If I do that, I should have theta all over 100. And with that, I can find the temperature at any other pressure apart from the upper fixed point and the lower fixed point. Just the same thing. In fact, this formula is so useful. It is the formula that we are going to use for all types of thermometer. We can even use it beyond. We can use it for more applications than just to find the temperature that is shown by a thermometer. We are still going to get there very soon, and we are going to see it. Now, that is constant volume gas thermometer. Other types of thermometer include thermoelectric. So before we move into other types of thermometer, let's take a question on constant volume gas thermometer. This question goes thus: what is one advantage of using constant volume gas thermometer for temperature measurement? It gives an accurate measure of temperature, and that is just it. In such a thermometer, that means in a constant volume gas thermometer, in one of such constant volume gas thermometer, the gas pressure at 0 is 200 millimeters of mercury. The gas pressure at 0 is 200 millimeters of mercury. And at 100, it is 270 millimeters of mercury. At 100, it is 270 millimeters of mercury. 270 millimeters of mercury. The question now is that, what is the room temperature if this produces a pressure of 214? What will be the room temperature? I want to find the room temperature, any other temperature that is used in the question apart from 100 and 0, I'll call it theta. When it produces a pressure of 214 at that temperature, it produces a pressure of 214 at that temperature. So we can easily just do pressure at theta minus pressure at 0 all over pressure at 100 minus pressure at 0 should be equal to theta minus 0 all over 100 minus 0. So just need to arrange this side exactly the way you have arranged this side. The only difference is here you have temperature values, here we have pressure values. So P theta is 214. I must ensure that they are all in the same unit. P0 is 200. P theta is 270. P100 is 270. P0 is 200. It must be equal to theta all over 100. So that should be 14 all over 70 is equal to theta all over 100. If we cross multiply, we have 70 theta is equal to 14 times 100. It means that theta must be equal to 1,400 divided by 70, and theta must be equal to 20 degrees Celsius. And that is the answer to the question. So we'll move on to thermoelectric thermometer. The thermoelectric thermometer employs the use of two dissimilar metals, two metals that are not the same thing. For laboratory purpose, we can use metals like copper and constantine. because those are metals that are usually wires that are usually available. But for industrial purpose, we have to think of the fact that there is now a possibility of measuring very high temperature. So we must use metals that have very high melting points, such that when they are used to measure the temperature of temperatures that are very high, they will not melt while being used. So it consists simply of a galvanometer. A galvanometer can measure very small amount of current. We can use a galvanometer or millivoltmeter. Millivoltmeter can measure the very small potential difference. Those are the two measures of electricity. It's either you are measuring potential difference, the voltage, or you are measuring the current. And because the current we are expecting in this case is very small, the voltage we are expecting is very, very small, we are going to be using galvanometer or milliammeter. They are the same thing, or I use millivoltmeter, something that can measure small amount of voltage. If we take a wire, if we take a copper wire and another wire, maybe Constantine, and we loop them together, if we put this inside a substance, let us assume that the substance is hot. Heat from the substance will be introduced into this wire, will generate current into this wire that can be measured by the galvanometer. And that is simply the idea that a thermoelectric device works. Thermoelectric, it measures electricity that can be produced from a temperature change. So there's a temperature change introduced at the junction between two junctions of two metals, and the galvanometer can measure the current that is introduced. If that is the case, we'll have this measuring the equipment. In other forms of a thermoelectric device, we can have one end introduced to one hot medium, another end introduced to a cold medium. While we have a junction of a metal, we can have two metals, one and the other is looped to an hot surrounding, while one and the other again are also looped to a cold surrounding. There's a galvanometer that they have been connected to, and with this, it's going to measure a potential difference that can give us a measure of the difference between the temperature of the two. Even if it is current that is giving us, it's going to measure a current value that will be a measure of the difference between the temperature of the two. So that is how it simply works. That is how a thermoelectric device works. The change in heat at the junction of two metals will generate very small amount of current or voltage that can be measured by a millivolt or a galvanometer. The amount of current or voltage that is measured by the galvanometer or the millivoltmeter, respectively, will give us a is proportional to the temperature that the junction connected to it have been introduced to. Now, there are also equations that we can solve using the knowledge of thermometric substances. We have some. Here, I've been given something of this form. This is said to be copper, while this is said to be Constantine. This end is immersed inside steam that is at 100 degrees Celsius, while the other end is immersed inside ice at 0 degrees Celsius. The other end is immersed inside ice at 0 degrees Celsius. We have at that point a reading of 4. There's 0, there's 4, there's 10. We have the pointer of this meter
showing us 4. Now, it is 4 millivolts, so we are using a millivolt meter. It is 4 millivolts. We are using a millivolt meter. The question is this. The figure above shows the junction of a thermocouple thermometer connected to a millivolt meter, which can read up to 10 millivolts. It can read up to 10 millivolts because that's the maximum. Now, when one junction is in ice at 0, and the other in steam at 100, the millivolt meter reads 4. It is reading 4 the way it has been shown. What is the maximum temperature which this arrangement can measure, assuming the cold junction remains at 0? What is the maximum temperature that it can measure, assuming the cold junction remains at 0? Now, I can also use proportionality to solve this question. The change in temperature here is 100, and it is giving me a voltage measure of 4 millivolts. 100 degrees Celsius is giving me a volt measure of 4 millivolts. Now, what temperature difference, considering that this remains at 0, what must now be the temperature that will be put here for this galvanometer to have a full-scale deflection? Because, of course, once it shows full-scale deflection, that is the maximum that it can measure. Full-scale deflection is the maximum value, and the full-scale deflection is at 10 millivolts. What will be the maximum temperature that will make it reach that 10 millivolts if for a 100-degree change is reading 4? I can use proportionality to solve the question. If I do that, that becomes 4x is equal to 100 times 10. It simply means that x is equal to 1000 divided by 4. If we divide 1000 by 4, we will have 250 degrees Celsius. And that is our final answer to this question. For resistance thermometer, we are just having a wire, and when we expose the wire to a change in temperature, we understand that the resistance of the wire will also change. We will now measure the resistance of the wire and also convert it to temperature. The only difference is the wire that is so used must be a wire that can withstand high temperature and must be a wire whose resistance changes linearly with temperature. That way too, I can use my extrapolation formula. I will expose it to a temperature of 0, I'll find its resistance. I will expose it to a temperature of 100. I'll find its resistance. Let me call that one R100. So I can now find its resistance at any other temperature that is given to me apart from 0 and 100. And with that, I'll be able to solve the question. We are going to see one question like that, just something very simple that we can work with, and we'll move on. We are told here that the electric resistance of the element in a platinum resistance thermometer, platinum is usually used as the for our resistance wire, because platinum, like I told you, has a very high melting point, so it can withstand very high temperature. Now, the electrical resistance of the element in a platinum resistance thermometer at 100 is 100. At 100, 0, and room temperature are 75, 63, and 64.992. The resistance at 0, the resistance at 100, the resistance at room temperature. They did not give me the room temperature. I will represent it with theta. The resistance at 0 in this case is 63. Resistance at 0 is 63.000. The resistance at 100 is 75.000, 75.000, while the resistance at the room temperature is 64.992, 64.992. If we do that, we have R theta minus R0, if I use my extrapolation formula, all over R100
minus R0 is equal to theta minus 0 all over 100 minus. That's still the only formula that I've been writing. Initially, I used length when I was talking about the liquid in glass. I used pressure when I was talking about constant volume gas thermometer. Now I'm using resistance because I'm talking about the resistance thermometer. Now, if I put those values, I will have 64.992 minus 63 all over R100 is 75 minus 63, and this will be theta all over 100. So if we subtract, we will have 1.992 all over 75 minus 63 will be 12 is equal to theta all over 100. And if we cross multiply, we should have 12 theta is equal to 1.992 times 100. That should be 12 theta is equal to 199.2. It means that theta will be 199.2 divided by 12. 199.2 divided by 12 should give us 199.2 divided by 12 should give us 16.6. It means for this question, the room temperature is 16.6 degrees Celsius. Now, the formula, this formula can also be used for more important things than just to convert a thermometric property to a temperature value. We can even use the formula to convert between Celsius and Fahrenheit, two major temperature units. I can use it to convert between Celsius and Fahrenheit by putting Fahrenheit on one side and Celsius on the other side. If I continue with the form in which I've been writing the formula, I can say that F at theta minus F at 0 all over F at 100 minus F at 0 is equal to, if I write the Celsius part, Celsius is the one that has 0 as its lower fixed point, 100 at its upper fixed point. So if I use something like this, so the corresponding side of the Celsius is the Fahrenheit that I've written here. So my F naught is the upper fixed point in Fahrenheit. F100 is the F naught is the lower fixed point in Fahrenheit. F100 is the upper fixed point in Fahrenheit. And F theta is the Fahrenheit equivalent of this Celsius temperature. This is the Celsius side and this is the Fahrenheit side. There are so many things I can solve between them. I hope you know that the melting point of ice in Celsius is 0. In Fahrenheit, if you don't know that before, let me give you as 32. Water freezes at 32 degrees Fahrenheit. And it boils at 212 degrees Fahrenheit. So the Fahrenheit at 100 is 212. So Fahrenheit at 0 is 32. So that should be theta all over 100. So this must be F theta minus 32 all over, if you subtract 32 from 180, from 212 you have 180, is equal to theta all over 100. You can either stop here. At this point, if you give me a Celsius value, I'll put it here, and I'll get its Fahrenheit equivalent. If you give me a Fahrenheit value, I'll put it here, and I'll get the Celsius equivalent. But we can simplify further by writing F theta minus 32. If I cross multiply, I will have 180 theta all over 100. 0 should cancel out 0. 2 here 9, 2 here 5. So I can have F theta minus 32 is equal to 9 theta all over 5. I can bring 32 to the other side such that F theta becomes 9 theta all over 5 plus 32. So this simply is a formula for converting every Celsius value to Fahrenheit, and I can also use it to convert Fahrenheit to Celsius. You don't need to cram it once you pay attention to the derivation. With that, we have come to the end of this very interesting lesson on temperature and its measurements. Please join us for our next class as we continue to make all other topics in physics appear simple. Thank you.